Hi everyone, it's your teacher Miss Mai, and I'm so sorry I can't be with you today to teach you some math, but here I am and hopefully you can learn something from the lesson. So in today's lesson, we are going to be talking about misrepresenting data. And what I mean by this is that sometimes when we create graphs or when we look at graphs, they can lead us to misunderstand them. And this is because graphs are visual components of math. And we can gather information by visually looking at the information presented to us. Now, what happens when that information is presented to us in a not so accurate manner? How can we figure out when it's misleading and when it's not? And so that will be what we will be looking at in today's lesson. Now, before we continue on with the lesson, there are two words that I want you guys to keep in mind and be familiar with, as I will continue to use these words throughout the lesson and throughout the unit. The first word is distort. Now, distort refers to a change in the appearance or maybe a twist in the meaning that could lead to misleading information. Secondly, the second word is majority. So majority means more than 50%. Now, let's look at our first example. Now, these two graphs that you see on the screen, they display the same data, but in slightly different ways. Take a moment to gather information from both of these graphs. How are the graphs the same? Well, you might have noticed that although they look slightly different, all the points are the same. The trend is also pretty similar, and in terms of the month in which we are looking at this data, they're all the same. Now, the graphs are different, and we can kind of tell because, one, when you look at the side, you will see that, oh, this scale is a little bit different compared to the scale of graph B. And so because the scales on the side are different, some of you might think, well, this graph looks like it's more zoomed in compared to graph A. Now, the information in both of these graphs are the same and they are both accurate, which leads me to my third question. Given what we know, which graph, graph A or graph B, seems to be a more accurate representation of the data? My choice on which is more accurate is actually graph A. And some of you are thinking, well, how come, Miss Mai? Let me explain. So in graph B, it is true that because it is a little bit more zoomed in, we can see the points and what value they are slightly better, a little bit more clear. And so that is a positive for graph B. However, graph B can be slightly misleading because for people who are quickly glancing at this data and they don't quite look at the scale quite yet, they might think that the sales in July were August and September were absolutely horrible. And part of it is because these dots are really close to the axis here. And so with the distortion of the scale, okay, creating the zoomed in effect, it might exaggerate the idea that the sales in the earlier months, July, August, and September, were all really, really bad. And that there was a upwards trend that was very obvious and very significant as we head into December. Now, this might not necessarily be true, and it might not be as exaggerated as this looks. And so we look at graph A and we notice that, yes, the sales in July, August, and September are fairly low, but they're fairly close to each other. And so there is an upward trend, but it isn't as exaggerated as we might think. And so I'm tempted to say that graph A is slightly more accurate compared to graph B. And so we'll be looking at graphs like this and just discerning and deciding which graph is a little bit more accurate. And so before I continue to move on in the lesson, you might have noticed that in the previous graph, Now, in the previous graph, you might have seen a break in the line. And this break represents a jump or a skip starting from 0 to the next biggest number. Now, I caution you guys to be careful if you choose to do this. If you're using line breaks in your graphs, only do so when the jump from 0 to the next number is very large and you want to skip a few, okay? But please be very careful and very cautious. If you are not sure when to use them, please make sure you consult with me before you use it. Okay, now take a look at these two data sets. So they share or they show these exact same data. Now, take a moment again. What is different between the two graphs, the graph on top and the graph on the bottom? You might have noticed that this time the scales are slightly different. Again, the top scale seems to be showing a more zoomed in version of the data compared to the bottom one. Now, based on what we have talked about already, which graph is better at comparing the data between the test scores of males versus females? And I'm hoping that you chose the bottom graph. The reason being is the top graph is very, very misleading. In the top graph, because it is zoomed in, it seems like there are big differences between the scores of the females versus the males. For example, we look at test number 1. In test number 1, we see a score for males. Now for females, there is no bar that is visible. Now what could that mean? Could it mean that the females just did absolutely horrible and got 0, or did no females write test number 1 at all? And then you continue to look and you look at test 3 and you think, wow, the females did really well compared to the males. Now that might not be so accurate, because when we look here at the bottom graph, we see, oh, actually in test 1, females did write the test, but maybe their score was 75 and that wasn't shown in the in the top graph. And you will notice that in the bottom graph, when we compare the two data sets of males and female test scores, we notice that there isn't that great of a difference between the males and the females. And so with the top graph, it is an exaggeration and it seems that way, okay, even though the data is the same. And so the top graph is very misleading. And so using data like the bottom graph and representing it in that way is much better and eliminates any exaggeration or could lead people to misinterpret the information. Now we can do so with this example. So take a look at Matthew's test scores. Here's graph A and graph B. So in graph A, you will notice that in test 1, Matthew scored 60. In test 2, he scored 65. Test 3, he scored 68. And test 4, he scored 69. Now, from this graph, it makes it seem like Matthew improved tremendously from test 1 all the way to test 4. Now, the impression is that, well, in test 1, he didn't do well at all, but he did pretty well in test 4. Now, let's take a look at the second graph that represents the same information. So in this graph, what's changed is the scale. And the scale in the previous graph created a more zoomed in version. And so this shows the information in a more clear manner. In this one, we see that, yes, Matthew's test score did improve and did increase as he did his respective tests. However, the increase is not as bold and not as large as the first graph seemed to show us. And so when we look at the first graph, you might be tempted to say, well, in the first test, he must have did so poor because that bar was so small and he might have even failed. Whereas in fact, Matthew did not fail and he got a 60%. And yes, he did improve, but again, it wasn't a tremendous improvement as exaggerated in graph number 1. And so it seems to be that in graph number 2, this is a more accurate representation of Matthew's test scores and his improvement between those tests. Now, misleading graphs can cause people to misinterpret the data and draw false conclusions. And so there are two things that usually lead to misleading information. And these features include distorting the scale. So changing the scale, creating a more zoomed in effect, can lead to people making false conclusions. Secondly, distorting the information by using visuals of different sizes. So we see here that skateboards, have 40 volts, whereas bicycles have 38 volts. Now that's only a difference of 2 volts. However, the bar for skateboards, because it is wider, it's a little bigger, it seems like so many more people voted for skateboards compared to bicycles. So be careful with distorting information by using visuals. And in a moment, I'll show you some examples of what I mean by that. Okay. So here, this has to do with distorting the scale. So if you look at the first graph, you'll think that Mario Crosby, over his 15 years, didn't do too well with scoring goals. Because one, due to the scale distortion and the line being so close to the axis, it gives the impression that he didn't do well at all, like close to 0. And not only that, his progression wasn't that great and that he was fairly consistent throughout his career. Now, if you look at graph number 2, the scale is slightly different. And so the scale starts at 0 this time, and we notice that, oh yes, there's actually a trend in goals he has scored over the years. Okay. Now, in graph number 3, the scale is slightly different. It is a little bit more zoomed in. And yes, we can also see that there are trends in the way he's scored over the years. Now, think about this. If you were to be given this data set, which graph would you use? And I hope that you had chosen this graph. The reason why it is not the first graph is, one, it is misleading and can lead us to think that Mario Crosby was a fairly weak player and didn't score as much as others. It is also very flat, which means that he didn't necessarily improve or anything like that over the years. So that can lead to false conclusions. Now, graph 3, although very similar to graph 2, graph 3 is a little bit more exaggerated, and it's harder to see the trends within graph 3. And so we see him improving and not doing so well one year, and then improving and then not doing so well the other year. And we see, yeah, there's a pretty big improvement here, but it's relative to this and it doesn't seem as great. Now, when you look at graph 2, you can see more of a trend that Crosby improved in the first few years of his playing. Now, over the next few years, there were some good years and some bad years, with his best years being some of his last ones. And this shows that trend a little bit more clearly. And last example for today is a pictograph. Now, this pictograph is not a good pictograph at all. And what you will start to notice is that for cats, there's the same amount of students that chose cats as their favorite pet as dogs. So students that chose dogs as their favorite pets also had the same amount. So each cat represents 10 students. So 40 students like cats. Now for dogs, each dog represents 10 students. So about 40 students also like dogs. Whereas for fish, there are only 3 fishes, and each fish represents 10 students, which means that only about 30 students like fishes. Now, the representation of this data is misleading due to the size of these symbols. So it seems, just based on the pictures, that most students, their favorite pet is a fish. Now, we might think that because the fishes are so big, and when we compare this line, the fishes are all the way out here. However, when we look back at our data, we realize that only 30 students like fishes. And same thing with cats and dogs. It seems like more students like dogs because the dog symbol is a little bit larger than the cat symbol. However, the number of students who like cats and the number of students who like dogs are the same. And so when we look at graphs, it is very important that we be careful of the scale and any distortion in visual imagery that could lead to false conclusions. In math, it is very important that we don't create any bias or we lead people to misunderstanding certain information. And so that is my lesson today. For the rest of the class, I would like you guys to work on the assigned problems. It is pages 23 to 26, numbers 4, 5, 7, 8, 10, and 13 to 16 in your textbook. Bye for now.